In this lesson, we're going to look at speed, velocity, and displacement. Now, we already know what displacement is, right? Displacement is the change in position of an object, but we need to remember that displacement includes direction because we're all familiar with speed. We know that speed is how fast something moves. Now, if you think about what that means, it's a comparison with time. Not only do we want to know how far something's going, we want to know how long it takes, which explains the unit of speed. 75 miles per hour tells me how long it takes to go 75 miles. In the SI system, we use meters per second. So how many seconds does it take to go how many meters, right? So speed is how fast something moves, and it is a comparison to time. And so we know we can calculate speed. Speed is equal to distance divided by time. But the problem is, distance does not tell me direction. And we're interested in not only how fast something's moving, but also which direction it's going. So we're going to need to be a little bit more precise than just speed can tell us. And so what we're going to do is we're going to use velocity. So velocity is going to be based off of displacement. Velocity is speed with direction. So it's displacement divided by time. Displacement over time. And of course, we all know that scientists have to be lazy and use abbreviations, right? So V is velocity. Remember, displacement is change in position. That's delta x over time, or actually change in time, the length of the time of the interval. So I'm going to go ahead and write delta t as well. So sometimes you'll see me write t, sometimes delta t, but it is the length of time for that interval. It is a duration of time. So velocity is displacement divided by time, which, like I said, means we're going to have units of meters over seconds. If you remember the unit of velocity, then you also remember the equation for velocity, right? Meters per second, displacement over time. Now, this is one equation, but because it's got three variables in it, we're going to be able to solve it for three different scenarios. So right now it's solved for velocity, but if I multiply both sides of this equation by delta t, let me show you what I mean. So velocity is displacement divided by change in time. If I multiply both sides by delta t, what I do to one side, I have to do to the other. And then what I get is these delta t's cancel, and I'm left with velocity times change in time equals change in position, or displacement is velocity times time. Distance equals rate times time. You guys have seen that equation before. We could simplify it a little bit if we take out that delta. Velocity times time equals displacement. This is probably the most useful one to memorize because you can divide both sides of the equation by velocity or by time to solve it for the other variable. This is the definition of velocity, though, so that's the one we start with. And so, like I said, we can divide both sides of this equation. If I divide by time, I get back to where I was, but if I divide by velocity, then I get that time, the length of time it takes to do something, to move some distance, is equal to that distance divided by that velocity. So those are three separate equations, all based off of the definition of velocity. They're all solved for different variables. You can get one from the other just doing a little bit of algebra. So we're going to use those in a later video to work some practice problems. But what I want to look at is how this relates to change in position on a position time graph. So remember, on a position time graph, we have where the object is and when it's there, which means we can figure out what's going on in between. So we have position, we have time, and we'll go 1, 2, 3, 4, 5 meters. 1, 2, 3, 4. We'll go 6 seconds. 1, 2, 3, 4, 5, 6. And we're going to put a couple lines on here to represent an object's motion. We're going to have that object start up here at 5 meters and then come down to 1 meter and get that done in 2 seconds. And then we'll go over to 4 seconds and not move, and then we'll come up to 2 meters in that last second. Okay? So, or last 2 seconds. So this is our position time graph, and it's showing us how the object's position changed through time. But it's also going to allow us to figure out the object's velocity for each one of those time intervals, because we can look at this and see, yeah, it's got a negative slope, it's moving closer, we know its direction, but we can also look at it and go, this part is steeper than that part, which means this is faster, and we can actually figure out how fast based off of our equation for velocity. So let's take a look at our first time interval. Our first time interval is from when we have a change in motion, from the beginning when we have a change in motion, which is there, right? So 0 to 2 seconds is our first time interval, and our initial position, or our position at time 0, is 5 meters. Our position at time 2, our final position for this interval is 1 meter. And so we can find our change in position, which is final minus initial. And when we get that, we have 1 minus 5, which equals -4 meters. It is okay that our change in position is negative. That just means it moved closer to the reference point. And what we then can do is say, okay, well, since velocity is change in position over change in time, it took 0 to 2 seconds, or 2 seconds, for it to go those -4 meters, which is -2 meters per second, right? So that means every second the object moved -2 meters, or it got 2 meters closer to the reference point. If that was a speed, it would just be 2 meters per second, right? That's how fast it moves. Every second it goes 2 meters. But the negative indicates which way it's moving. Now, for our next time interval, so that's our first time interval. Our next time interval, we're going to go from 2 seconds to 4 seconds. This one's a little bit different because our initial position, which is now at time 2, is 1 meter. And our final position, which is at time 4, is also 1 meter, which means our displacement is 0, right? It started and ended in the same spot, but the same equation still works. Now our change in time, 4 minus 2, right? 4 minus 2 is 2 seconds. Now what we're going to do when we get our velocity is 0 divided by 2. Well, 0 divided by anything is still 0, right? So this is 0 meters per second. It's not moving. So it's got no velocity. It's at rest. You wouldn't actually need to show me the math to show me that you know it's not moving, right? If the position isn't changing, the velocity is 0. So that's our second time interval. Now let's take a look at our last time interval. Our last time interval is from 4 to 6 seconds. And from 4 to 6 seconds, we started at 1 meter, and we end at 2 meters. So our final position is 2 meters, which means our displacement is 2 minus 1, which equals 1 meter. So this thing moved positive 1 meter away, right? It started close and moved further away. There's our displacement, and it took our change in time, 6 minus 4, is 2 seconds. So when we get our velocity, 1 divided by 2, this is equal to 0.5, or 1/2 of a meter per second. So that means it's moving away 1/2 meter every second, which isn't very fast, right? It's going this far every second. Compared to what we started with at the beginning, 2 meters per second, it was going quite a bit faster. But this one's positive because it's moving away. So we already knew positive slope means it's moving away. Well, because that's a positive slope, it's also a positive velocity, and positive velocity means it's moving away. Which means the last thing that we're going to write down for this is the slope of position time. The slope of a position time graph is velocity. So you can calculate something's rate of change of position, you can calculate its velocity based off the slope of whatever interval you're looking at on your position time graph.